Um, so this talk is about normalizing flows, and this topic lies at the intersection of applied probability and deep learning or neural networks. And this being an applied probability meeting, I thought I will not make any assumptions about the background on neural networks. So I'll spend some time introducing neural networks and some of the relevant things, but this also means that I'll not be able to go into the proofs. So I'll mainly be defining things and stating theorems and giving general background. But I hope that's a reasonable trade-off. And please feel free to ask me any questions at any time. Okay, so normalizing flows, what are they? They are a recent neural generative model for learning probability distributions. I'm going to define all these terms, but first let's see what's the problem of learning probability distributions that these models solve. Okay, so the problem of learning probability distributions is we are given some unknown random variable x in d-dimensional space. And we assume that it's a nice random variable, so it has a probability density function which does not fluctuate too fast and so on, right? So it does not do anything pathological. And we have independent identical samples of x. And from these samples, we want to learn an approximation to the density of x, okay? And if you can do that, then you'd like to be able to do the following. You'd like to generate new IID samples of x, possibly with some conditioning on some events also, but for the moment, we can just say generate samples of x. And also estimate the density, the density function p sub x of the random variable x at any given point. Okay. So in applications, often the dimension d of the space is very large, but in this talk, I'll mostly focus on d equal to 1 case. So this is for two reasons. One is for simplicity. In normalizing flows, the d equal to 1 case is really special, and d greater than 1 is considerably more complicated. But also there are theoretical reasons for that, which I'll mention later on. Okay. So the problem of learning probability distributions is a classical problem in statistics. It goes back to Gauss, who tried to fit Gaussian distribution to data, and Pearson tried to fit mixtures of Gaussians to the data. And many other classes of distributions are used, exponential families, graphical models, and so on. And there are many general methods for doing it, method of moments, method of maximum likelihood, and so on. But the new neural methods seem to do better in modern applications. So let me just briefly mention what these modern applications are. So many of these applications involve perceptual data, something that we can recognize with our senses. So images, video, audio, so on, but also non-perceptual data like molecules, graphs, DNA, sequences, text. So let me give a few examples of images. I won't give examples of the other types of data sets. So here is the well-known MNIST data set. Here, each digit image is a sample. And each image is a vector in 784 dimensional space. Okay, so it's pretty high dimensional. Here's another data set called Fashion-MNIST. Again, each image is a data point in 784 dimensional space. Here's a celebrity photos data set. Here, each image is in space of dimension 256 times 256, or possibly even higher. So these are very high dimensional spaces. What do we understand about these data distributions? So they do, as we saw, they live in very high dimensional space. But the problem of learning probability distributions without further assumptions is clearly hard. One can easily prove that this cannot be done. One needs exponentially many samples in exponential in the dimension and so on. So one needs some assumption. But here we don't really know what these distributions are, and we don't have a good characterization. But there are some informal things we can say. For example, people believe that intrinsically the data behaves like a low-dimensional manifold. It's close to a low-dimensional manifold. or it has no complexity in some other sense. Although none of these is a formal statement. And this is what presumably allows us to learn these distributions. Non-neural methods don't work so well on these distributions. How well do neural methods work? So let's see that. But before that, let me very quickly enumerate the main types of neural generative models. So there are variational encoders, generative adversarial networks, or GANs, which were discussed in the previous talk briefly. These are very famous. They generate very good quality samples, but they don't provide density estimation. So that was one of the two things we wanted to do. One was generate samples. The other was estimate densities. They only do generation of samples. And then third is the normalizing flows model, which is the focus of this talk. So each of these is a class of models, and there are lots of models within each class, tens or even hundreds. But I'll just focus on normalizing flows for this talk. So let me just show what normalizing flows can do with two examples. So on the left here is the output of normalizing flow model that was trained on Celeb A dataset that I showed earlier. And these here are the outputs, output samples from this dataset. So these are not real people, these are generated by the model. And on the right here, each image on the top row depicts a random variable in 2D, the density of that random variable. So if a point is brighter, that means the density is higher, and if the point is dark, then the density is low. And on the bottom row, what we see is the output, the density that the model learned. So this seems to pretty faithfully reflect the input density. Okay, so this seems very good, but how well do these models really work? So to visual inspection, it seems like they do very well. However, rigorous evaluation of this is very hard, because how can we evaluate these things? One, perhaps the simplest way would be to compute the probability distance between the learned distribution and the data distribution, right? But this is hard given the high dimension. But maybe since we believe that these are low probability distributions, one can do that. But this remains a work in progress. Other axes along which these models are evaluated are training data set size, how many samples we need, and how much computation is required for training. Neural models tend to require a lot for both of them. Okay. So as was said in the previous talk, GANs are black magic. Neural normalizing flows are also black magic, and we want to take the magic out of these things. So we would like to theoretically analyze these models. So generative models fall under unsupervised learning, but before, which is harder, and there's something called supervised learning, which is presumably easier. Certainly, it's much better studied and relatively much better understood. So I'm going to talk about supervised learning a little bit, and also neural networks, how neural networks are used to solve, how they are applied to supervised learning. Okay, so yeah, let me briefly pause here and say where we are. So I introduced the problem of learning probability distributions, and I briefly touched upon neural generative models. I'm going to give a very quick introduction to supervised learning problem neural networks. Then I'll give a brief sketch of what we understand about about neural networks for supervised learning. Then I'll get to define normalizing flows based on what we cover. And I'll state our theoretical results for normalizing flows. Okay, so here's the supervised learning problem. So there are two ingredients. There's a function capital F from d-dimensional space to reals, which is unknown. And again, we assume that's reasonable, meaning it's not very, it has derivatives when needed, and it varies reasonably smoothly. And D is a non-probability distribution, data distribution on the D-dimensional space. So here in cyan, I'm depicting for D equal to 1. In the D equal to 1 case, so the cyan curve is the function f. Now we are given labeled data points. So we sample xi's, x1 to xn from the distribution D. And for each xi, we provide xi and f of xi, which is the label of that point. So this is the main difference from unsupervised learning, where we don't get any labels. Here we get labels. And so here in this picture, by blue points, I've depicted these labeled points, which lie on F. And our task is to construct an approximate representation H of capital F from this data. So how can we measure how good is a representation reconstruction H of F? The two measures that I used, one is test loss, which is the expectation of H of X minus F of X squared. But this we cannot compute because we don't have access to D. The other is training loss, which is basically the same thing, but it's empirical version of that. So it's sum of H of Xi minus F of Xi squared over the sample points. So ideally, we would like H to be equal to F, but we may not have sufficient information to achieve that. We can only hope to do that where D puts sufficient amount of data points, right? So, which is okay. So, which is also our test loss will be small as long as H is a good approximation of F on where D has some probability. Okay. So then the question is how to construct H with small training and test loss. That's the supervised learning problem. So a purported solution involves two main elements. One is we need to give a class of functions from which our function H will be drawn. So people use, there's a very large set of classes that are used, some of which I have listed here, linear functions, polynomials, decision trees, and so on. Neural networks are one of those. So we'll be working with neural networks. So our functions, candidate functions H, which we use to try to approximate F, will come from neural networks. The second element we need is training. So given this class of functions, how do we choose the one that's a good approximation of F? So that's the method to fit to the data. So I need to specify these two things to say how neural networks are used to train, to solve supervised learning. Okay. So here, first I'll say how neural networks, what a neural network is. I'll only describe the very simplest types of neural networks. So these are one hidden layer networks with a scalar output, right? So the input is a d-dimensional vector x, and the output is n of x, which is given by this formula. Let me explain this. So the neural network has a number of parameters. One is m, which is the number of neurons, number of semands here. And each semand is of this type. AI, which is a scalar, times sigma of wi transpose x plus bi. Each wi is a vector, and each bi is a scalar, right? So it's a simple formula. So you take a dot product of x with the weight vector wi, and sum with bi, apply a function sigma, which is called an activation function, and I'll explain this a little more in the next slide. And sum these things up with AIs. Okay, so that's all a neural network does, one hidden layer neural network. These are also confusingly called two-layer networks, but two layers, no, not two hidden layers. Okay. So we can represent these functions more compactly in this way. So A is a vector now, m-dimensional vector. So A transpose times sigma applied pointwise of wx plus b. W is the matrix of which has wi's as the rows. And this construction can be repeated. So output of the first layer can be fed into a next layer and so on. So that can be used to define higher depth networks, which I'll not try to define very carefully. Okay, so So n of x here defines a function given if you choose any sets of w1 to wm, a1 to am, and b1 to bm, then that gives us a function, right? So each choice of these weights defines a function, and that gives us the class functions from which we'll choose our h. Okay, here let me quickly say what the activation functions are. So traditionally, people used activations like sigmoid or 10h. I've drawn 10h here. Currently, most popular is ReLU, which is even simpler. It's just the maximum of ReLU of t is just max of t and 0. Okay. Many other functions have been proposed, which also work better than ReLU sometimes, but there's nothing that works the best. Right? But ReLU is by and large the default. And these are nonlinear functions and in fact non-polynomial, and we'll see why in the next few slides. Okay, any questions? All right, so let me now say how we use.
There's one question. So
yes, please go ahead.
So this is from Kayada. It says small data sets give good accuracy in training sets. So one can get good accuracy, but will it be helpful for test data?
I'm sorry, can you repeat?
Yes, it's in the chat. So the small data sets give good accuracy in training sets. One can get good accuracy there, but will that be useful? Helpful?
Yeah, that's a problem. For neural models, no. It depends on the model, it depends on the problem, but for neural models, small data sets are not good enough. They are really data hungry.
That's
okay. So I described the class of functions from which we will draw our candidate functions, and I'll describe how to fit neural networks to data. Okay. But first, we need to answer this question: is the problem solvable in principle? Can a neural network approximate the given function f? Right. So the answer to that is yes. So this is the well-known universality theorem from the 80s and 90s. So it says that any continuous function f from a bounded domain, here we take 0, 1 to the d, but you can take any bounded domain to reals, can be well approximated by one hidden layer neural network with sufficiently large bits, so sufficiently many neurons. So m is sufficiently large, right? Or more formally, for any epsilon greater than 0, there exists a neural network, so which means that there exist weights for it, the w, a, and b, and m, so that n is within epsilon of f for all x's in the domain. Okay, as long as the activation function is not polynomial, because polynomial, if activation function was a polynomial, then the output is also a polynomial, and we know that there are functions that are not polynomial, so that's why we need it to be non-polynomial. Okay, so at least we know that neural networks are capable of representing functions that we want them to represent. But this theorem does not tell us two important things: how large does the width need to be for a given situation, and how to find the weights and biases in such networks. Right? So that's the training part, and that's what I'll describe next. So since we don't have test loss, we can try to choose weights and biases to minimize the training loss, right? Which is basically n of xi should be close to f of xi. And this can be done in multiple ways. For example, you could use nonlinear programming or sometimes even linear programming, depending on what your activation function is and so on. But those things only minimize the training loss and don't give a small test loss. Instead, if we use the following gradient-based method, which is very simple, then often we also get small test loss, right? So I'll just say, give one setting that often works. So we initialize the network randomly. This is initialization that's often used. So each vector, the weight vector is chosen from Gaussian distribution according to using some variance, specific variance. And we just do gradient descent on the loss function. So this is the loss function, the test loss, and we just do gradient descent on that. And I just wrote W here, but this is a function of W and B, and we do the same thing for A and B. Okay, and then two surprising things happen. The gradient-based training works. It gives you small training loss and also gives you small test loss. So why are these things surprising? Let me say that. The training loss is in general a non-convex function of the weight. So the loss that I wrote down previously for a neural network, that's not a convex function. That the situation looks like this for training loss. And what we want is a global. But the gradient descent method or gradient-based methods only work for convex functions. For non-convex functions, there are no guarantees. It can potentially get stuck in local minima for non-convex functions. And what we want are global minima. But in practice, the previous method still seems to do very well. So that's why this is surprising. Here is just a picture of a visualization of a real neural network. And you can see that it's highly non-convex, but what we would have liked is something like this. Okay, so that's one mystery. The other mystery is that we minimize the training loss, although our real objective was the test loss. But it often happens that even test loss is small for what we get, right? So the cyan function, in cyan is the function that we really want. In purple is the function that we actually get from training. And red is a function that has small training loss, but large test loss. But we don't get the red function, we often get the function purple. So that's the other mystery. So how do we explain this, right? Why do we get good generalization performance? Why do we get small test loss? So there's an informal conjecture here, which is that these algorithms are biased towards simple functions, meaning the neural net first fits simpler functions and then tries to adapt more and more to the data, but starts with simpler functions. So it won't find the red function in the previous picture. It will first find something simpler that fits the data. So what is simple is not quite well understood. That's one problem with this. The other is it's not quantitative at this point. But also, it's not an end-to-end explanation in the sense that even if this was true, why is there a bias towards simpler functions? So what we would like to do is perhaps prove a mathematical theorem that shows that this is what will happen, at least in some settings, right? There's also the question of when does this thing work? What's the real, what is the data set for which we expect this to work? So these things don't work for all data sets. I'll mention that. So I said neural networks work very well, but there are also problems with them. There are a diverse set of applications from classifying images to plotting folding, but it's largely a heuristic method. There are many well-known limitations. They are susceptible to adversarial examples. They don't work well on out-of-distribution examples, require a lot of data. And there are also provable limitations. They can't learn things like parity functions. So this cartoon is, although this is for machine learning, but it's even more true for neural networks, I think. Okay, so having said all that, let's see what we know about the theoretical understanding of supervised learning. Okay, so so there are three basic questions: expressive power, why and when are neural networks able to represent the data? The universality theorem that I mentioned has the problem that it does not talk about the size of the network. So this is one question. The other is optimization. Why are neural networks able to fit the data? Why does the training loss go to zero? And the third is generalization question, which is why do they give a small test loss? Okay, we will formalize this question the usual computer science way, where polynomial time and polynomial size are small and so on. But even in my mind, even right formalization, we may not have presently the right formalization of these problems. So even that's something one should think about. But we'll go with what the community has currently settled on. Okay, so so I'll mention basically what we know about this problem at present. So a couple of groups around the same time, building on previous work, essentially proved this result, that The gradient-based training, as I described in the previous slide, probably converges efficiently, efficient again in some polynomial sense, with small test error. If the neural network has the following properties: it has one hidden layer, it's highly overparameterized, which means it's very large compared to, it's not a very well-defined term, but it's very large compared to the parameters of the problem, let's say. And there's a careful random initialization. One can also consider the case where the limit, the width of the network goes to infinity. And that also one can analyze. And this is called neural tangent kernel, or NTK. So why does this happen? Very briefly, let me just say there's something like central limit theorem involved, because when you, even if you have a complicated random variable and you take an average of lots of copies of it, you get normal distributions, things become simpler. So something similar happens here, although I'm not going to go in any details. So presently, this is the only setting for which we have rigorous end-to-end results. Okay. So in particular, the following questions are open. So if we want to analyze moderately sized networks, which are not very large, not very highly overparameterized, then we can't do that even for one hidden layer. And the reason to do that would be that these tend to be better, actually, compared to very large networks. The other is analysis of deeper networks. So what we are talking about is only one hidden layer so far. And as you add more layers, things often the networks do much better. Both their expressive power improves, also generalization improves, at least to some certain depth.
There's a question by Devavrat Dobashi about the Du et al. Paper. Is the final layer fixed randomly and not trained?
You can train it too. They can do both.
And there's
sorry.
And then there's a comment about it depends upon. Maybe you can unmute yourself and ask the question.
The second part was that there is also some implicit assumption, or it's in the setting where the weights don't change too much, the so-called lazy regime.
That's correct. That's where this highly overparameterized thing comes in. And I forgot to put one more point, which is that the learning rate has to be very small. Right. So I put three conditions. There's one more condition, which is learning rate is small, which guarantees what you're saying, lazy regime or NTK. Yeah. Does that answer the question?
Yeah.
Yeah, so this is all in lazy regime. Also, Du et al. Can train A, but Ellen Zhu et al. Don't train A. But I'll be focusing on Ellen Zhu et al.'s result here, because they are the only ones that prove generalizations. Other papers mostly prove that training error goes to 0. Okay, so
there's one more question
yes?
from about how does one decide whether one should use gradient descent or Adam or other optimization algorithms?
As I said, it's more of an art than a science.
Yeah.
So you try things out. I think that's the best answer I can give. All right. So I'm going to just state this result. I'm not going to be able to prove it. This is from Ellen Zhu et al. This is again for one hidden layer neural networks. So we have this unknown function f that generates the data. F is a low complexity function. They have a specific definition of complexity, which I'll not go into. But for this, let's say f is given by a polynomial of degree at most 10, and the coefficient's not too large. So that makes the complexity small. But they can handle other functions as well with low complexity. Then you generate the samples, as we said before. D is any distribution. And then we have this neural network to learn. Which has one hidden layer, random initialization, which I'll not fully describe. It has ReLU activations. So this is important. It doesn't work with other activations at present. With M equal to 1 over epsilon neurons. Epsilon is any constant which will determine the final error. So you fix any epsilon, and M has to be at least 1 over epsilon, omega 1 over epsilon. And we train using a gradient-based method with small learning rate, which is like 1 over epsilon m. Since m is large, omega 1 over epsilon. It's actually, there are other terms that I didn't include here. So eta tends to be small. So after t equal to poly 1 over epsilon steps, with high probability, the neural network that you get has small test loss. Right? So this nt of x is the neural network at time step t, and test loss tends to be very small. So I've simplified the result a lot. It's much more technical, but this is the essence of it. Okay. So we will now move to normalizing flows. I had some proof outline, but I don't think I have time for it, so I'm going to skip it. All right. So where are we in the talk? I just learning probability distribution, generative models, and supervised learning neural networks, and theoretical analysis of those things. Now I'm finally going to define normalizing flows, for which I needed all those definitions. Okay. So I'm going to stick to d equal to 1 case. I'll make some remarks on higher d later on. So let's say x is the random variable which describes the data, unknown random variable. We'll assume that it's supported in -1 to 1 interval, which is essentially without loss of generality. So I'll make that assumption. And again, we assume it's kind of nice. Then we have a second random variable, z, a base random variable, which is going to be a standard random variable like the standard Gaussian, or the standard exponential distribution. So we know everything about z. And some notation, p sub x is the density of x, p sub z is the density of z. And now there's this theorem in optimal transport. So under some regularity assumptions on x, it is known that there exists a unique invertible differentiable function f from -1, 1 to the r. So that the random variable f inverse of z has the same distribution as x. Okay. So this is not really a hard theorem, and I could have given intuition for this if I had a little bit more time. But it's also not immediately obvious, probably. But it's not a hard theorem. But I'm going to skip it in the interest of time. But this theorem underlies the whole construction of normalizing flows. So basically, just to repeat, we can get x out of z by applying a function f inverse. There is a invertible function f, which with this property. And since we are in one dimensional case, invertibility is the same thing as monotonicity. So f is a monotonically increasing or monotonically decreasing function. And we're going to assume it's monotonically increasing without loss of generality. Okay. So if we had such a function f, suppose we had access to this f, and also f inverse, suppose we could compute these, then we would have been able to solve the problem of learning probability distributions as follows. So if you want to generate a sample of x, we simply generate a sample of z and apply f inverse, and that gives us the sample of x. Density estimation is also easy. There's a simple formula for using change of variables. The density of x, px at little x, is p sub z of f of x times f prime of x. This is the derivative, x derivative of f. This is a standard formula, right? So if we had access to f and we could compute derivative of f, then we can also compute the density p sub x at x. So then the problem reduces to estimating capital F. Okay, so how do we get f, capital F? So what we have is the density pz. We know everything about z, but we only have IID samples of capital X. So how can we estimate f? There are no labels, unlike in the supervised setting. So we need to measure goodness of a neural network. How well does it fit capital F? So for that, we go back to the method of maximum likelihood from classical statistics, which basically does the following. You work with a class of probability distributions and choose the distribution from that class that maximizes the likelihood of the observed data. So I'm going to make this precise on the next slide. And in this provably recovers the right distribution when we have sufficiently many samples. Okay. So let me first define the class of densities that we get for normalizing flows. So let me define P sub Fz is the density function of F inverse of Z, where F is a monotone function from the interval -1, 1 to reals. Okay. So we take any monotone function of this type, and for that we can define the random variable F inverse of Z, and that has density this, which is simply given by this formula using change of variables. Okay, so this is the class of random variables or densities with which we work, from which we try to find the one that fits the data the best. Now we want to choose F that maximizes the likelihood of the data, right? So what is the likelihood? It's just simply the product of the densities at the data points. So we want to choose F that maximizes this, or equivalently, we maximize the log of this, which is this L of F. It's a function of F, sum of the logs of the probabilities. So informally, the probability this has is that for F that maximizes L of F, we expect that little f tends to capital F, and the density also tends to P of X, assuming that the class of densities we are looking at also has the target density in it. Okay. So let me just rewrite here the log likelihood using the formula that we had. So we can write it this way: sum of log of z density of f of xi and the sum of log of f prime of xi. So this is a function of, or a functional of f, L of f, right? So we want to maximize this where the space, we are optimizing over monotone functions f. How can we do such an optimization? So this seems a little hard, at least in practice. One could apply things like calculus of variations, but it's not very clear how to do it with real data sets. So the idea, one of the ideas behind normalizing flows, or much of deep learning, is whenever you need a function which you don't know what to do with, or you don't know it, use a neural network, right? So which is what we do here. So we substitute n for f in the previous formula. So we get L of n, the log likelihood of n is the same formula as before, except n replaces f. So n, as you remember, so we are working with scalars now, right? So I removed the dot product here. There's no transpose. Everything is scalar. AR is a scalar, WR is a scalar, X is a scalar. So n of x is just this number. N prime of x, which is the x derivative of n, is just this number. Okay, so you can see that this is an explicit function of w and a and b. So if we take z to be standard Gaussian, then the objective function becomes n of xi squared and plus sum of log of n prime of xi. Okay, so L of n is an explicit function, and we can try to apply gradient-based optimization as we did previously for supervised learning and be done, right? But we are not really done because the function that neural networks represent are not monotone. And our whole setup depended on the function being monotone. So it does not work. It fails if we use n of x just like we did here. This thing does not work. We need to somehow ensure that n of x is monotone. Okay, so this is what I just said. The neural network architecture here does not guarantee that the function n computes this monotone because, for example, Even though sigma is monotone, that's a ReLU, we are using ReLU or 10H. But if we make WR negative and AR is positive, then this is a decreasing function of X. Right. So in general, N of X is not a monotonically increasing function of X. So the other idea that's used in normalizing flows is to tweak the architecture so that it does give us a monotone function or invertible function. Oops, sorry. Okay. So how do we do that? So that turns out to be somewhat involved. And again, I'm going to restrict to d equal to 1. So there are actually many methods to do that. There are two classes of methods. One is constrained normalizing flows, and most models are of this type. I'm going to describe one of these methods. And the other is unconstrained normalizing flows. There's only one paper that does this, which I'll also describe. Okay, so constrained normalizing flows. So we will assume that sigma is strictly increasing, which is the case for most activations. And what we'd like to do is, if we can somehow ensure that AI and WI are positive for all I, right? Then our whole neural network is monotone, because each individual neuron or summand here gives us a monotone function. Because WI is positive, so this WIX plus DI is an increasing function. AI is also positive, and sigma is increasing. So if you could ensure this somehow, then we would get at least a monotonically increasing function. So the main idea here is to just reparameterize. Instead of AI and WI in the neural network, we use AI squared, WI squared, which are always positive, whatever the values of AI and WI, right? So we define this modified neural network and constrained X, which is basically the same thing, except we are using AI squared and WI squared. So this is guaranteed by construction to be monotone. And then we just optimize this, the log likelihood of NC as a function of WA and B to get the trained model. And once we get NC, trained NC, then we can use it to generate samples, as we said before. So NC inverse, given a network NC, it's easy to invert it in 1D. You can do simple binary search and invert it. So yes.
There's a question about ReLU by Devavrat.
Yeah.
So is it, can you not use it just because of practical issues, or is it for analysis?
There is a real issue. I won't be able to go into it, but basically, yeah, actually I can explain. So in the log likelihood expression, we had an f prime of x, right? And when we have, if we use neural network, so we need to compute n prime of x. If it has ReLU activation, the n prime of x becomes a discontinuous function, right? So then it does not work. Your loss function becomes discontinuous, and the gradient-based methods don't work both in practice and also in theory. So that's why we need to go with something that has at least first derivative, which is continuous. Okay, so once we have trained NC, we can use it to generate samples of X, and also we can estimate the density.
So there are also a couple of questions about that. So about the transformation. So actually, there's an earlier one by Sandeep about if that generalizes to multivariate setting. This
it does. There are theorems. The things like Noether map and Brainier's theorem. So it does generalize.
And the second question on the same is by Samantak, which asks, how does the choice of the base distribution affect the method? So instead of
so that does matter. So our theorem, which I'll hopefully state, is not about Gaussian distribution, because Gaussian distribution causes issues for the thing. We instead use exponential distribution, which works just as well as far as we know in practice. But normally people only use Gaussian, as far as I've seen.
And
but there's no real good reason to stick to Gaussian. It's just something that we are used to probably.
And then there's a question. There are a couple more questions. One is about how does the monotone assumption, this is by Prabhu too. How does monotone assumption translate to higher dimensions?
Yeah, that's. I'm not going to be able to go into that because that's kind of complicated and we don't have time for it. But there are, as I said, there are things like Knothe map, Knothe's theorem, and Brenner's theorem, which have various versions of monotonicity.
And
yeah, that's all I'll say.
And there's a question of Pratik about it just says non-differentiability at 0. So Pratik, can you maybe unmute yourself and ask what the question was?
No, I think he answered about ReLU. Yeah,
okay.
I'm done.
Okay. So that was our question.
Okay, so this thing works quite well in practice, even with one hidden layer neural network in 1D. So here is an example of example run. So this is the input density and this is the output density. Okay. So I have about how many minutes do I have, Piyush? Piyush?
Sorry, I was unmuted. So we wanted to finish at 7:20, but we can go on for a little while more because we had a lot of questions. So
okay, so I'll try to finish in next 6-7 minutes.
Yeah, that's
7-8 minutes. Okay. So I just defined one type of normalizing flows, constrained normalizing flows. The other I said is unconstrained normalizing flows, and these are a little bit harder, but unfortunately I'll have to go fast. So the basic observation is that monotonicity of f is equivalent to the derivative of f being positive for all x. So what they use is instead of representing f using a neural network n, they represent f prime using n with the property that n of x is greater than 0 for all x. So this is how they do it. N of x is some function phi, which I'll define below. Phi of the previous neural network that we saw. Okay, so you define any general neural network, but then you apply this function phi to it. So sigma, the inside, the activation inside is going to be ReLU still, unlike in the previous case where it couldn't be ReLU. And phi is a real-to-real function, which is given by this formula. This is exponential if x is less than 0 and x plus 1 if x is greater than or equal to 0. Here is a graph of that function. So this has several nice properties, but the main property we need to talk about here is that p of x is always greater than 0. So since we have this, so n of x is always greater than 0, so f prime of x is always greater than 0. Okay, but this might give us f prime, but what we need for normalizing flow is f, right? So how do we get that? So it's a very simple idea again. So we represented f prime using n. To get f, we just use numerical integration. Right? So this is a picture of how we do numerical integration, right? Which we learned in high school or high school calculus. So f of x is just some step size delta times the sum of f prime of -1, f prime -1 plus delta, and so on. And this is an approximation of f. And since we are using neural networks, so instead of f prime, we use n here, and that gives us a new new network, which I'll call nu of x, right? So this is really going to play the role of capital F, or sorry, of f. So this is we substitute this in the log likelihood, so L of n of n u, and so this is then a function of W, A, and B, which we can optimize using gradient-based method.
There are a couple more questions. So
yes.
How do you go from the neural network for the derivative to the one for f prime to from?
So this is exactly what I'm saying here in idea 2 or below this, right? So we set up this function nu of x, which is written this way, right? Delta is some number that we choose, which I'll describe later. but you fix some delta to be some small constant, right? Let's say 1/100 or something. So once you have done that, then this is a well-defined formula, right? So you just substitute this in the formula for log likelihood, and that gives you a function of W, A, and B, which you can optimize.
And given that I'll have another. So does the quadrature rule matter, or like?
It does. It actually matters. So what I'm talking about here is the simple quadrature. In their paper, they use something called much more sophisticated quadrature, and that speeds things up. But it's harder to analyze things for that because that makes things non-convex in the analysis. That's the problem.
And there is a question by Sandeep about how does the approach perform in large dimensions, and there's a +1 from him, which I guess is for Sandeep's question.
Yeah, I'm going to briefly touch upon that in the next slide. Yes. Yes. So normalizing flows for d greater than 1. So whatever I said, right, the whole general construction I said, sort of more or less applies to higher dimensions, although it gets much more complicated. So in particular, we know that this invertible transformation exists even in higher dimensions, and there's various nice properties. So using that theorem, we can try to design neural networks, but it's more complex. So what do we know about it theoretically? I'll talk about that in this slide. So first, so these are our results. So for constrained neural normalizing flows, we give evidence that significant new ideas are needed even for d equal to 1. So what happens is that if your underlying network is very large or parameterized, then the training fails, both in theory and in practice. Right? We give theoretical reasons why it cannot work. And but if you use a network that are not very large, then it does work quite well. So it seems like we need to understand first supervised learning of moderate sized neural networks, which has been open for quite a while. So that's why I say significant new ideas are needed. Okay, so that's for constrained normalizing flows. Again, for d equal to 1, for unconstrained normalizing flows, we can analyze them when they are over-parameterized and show that they learn probability distributions. Now, I'll try to maybe state the theorem if I have time. And finally, for d greater than 1, again, we give evidence that significant new ideas are needed. So what that means is that to analyze those normalizing flows, we either need to solve supervised learning for moderate sized neural networks, which is open, as I said earlier, or we must solve supervised learning for more than one neural layer, which is again open. So there are these are sort of barriers that we encountered in analyzing d greater than 1. So I should say that for d equal to 1, the problem is in some sense very simple because we can solve it using at least computationally, it's very simple because we can solve it using histograms. But of course, it's not clear what neural networks do, normalizing flows do, even in d equal to 1. So that's interesting. Okay, so I can state the theorem if I have time, or I can just conclude here. It's a little bit of a mouthful, so it will take me some time to state it.
Yeah, we can go over the theorem.
Okay, all right. So let me backtrack. So this is again a simplified and formal statement. I'll take some liberties here, so it's not fully true in some sense. So you fix an epsilon greater than 0, fix a data distribution of random variable x, and we have these samples x1 to xn, and let f be the function that we really want, right? So that f inverse of x gives us the random variable z, which in this case is exponential, not Gaussian. We cannot do it with Gaussian right now, although I think it should work even with Gaussian. Then C of f is a complexity measure which tracks how fast f oscillates. So if f varies very fast, then C of f is large. Otherwise, if it's kind of smooth, then C of f is small. And now our neural network is over-parameterized, which means that M is at least C of F over epsilon squared. Number of samples is also large, C of F over epsilon squared, and number of quadrature points is C of F over epsilon. So now if you have this much time, this number of steps in the gradient algorithm, log M over epsilon squared, it should probably be theta here, not big O. Then if this is the function that we obtain at time step t after applying the normalizing flow, then we have this guarantee. The probability at least 0.9, the KL divergence between the target density and the density that the network learned is small, at most epsilon. Okay, so they are at least close in some sense, in KL divergence sense. And using Pinsker, you can also show that they are close in the L1 sense.
So there's a couple of comments, and I think
right.
Close with that. So one is by Devavrat, Devashi, which says that it goes against the common wisdom that you need heavily over parameterized networks.
Sorry, I didn't mean this result. I meant the previous one where it was the other direction for the constrained neural network.
So can you repeat the comment? What goes against wisdom, conventional wisdom?
No, your previous result you mentioned about constrained neural networks that do not work for over-parameterized.
Yeah, that's true. That was surprising because we spent a lot of time. We were sure that it would work, and then we kept running into trouble, and then we realized it cannot work.
And the last one is from Prabhu, which asks about the sample complexity for generating multivariate Gaussian using normalizing flow versus sparse and window.
I don't know. Right now our results are very coarse, so we can't. We can only analyze d equal to 1, and I don't know the answer to that. Okay, so that's the theorem, and let me just state these problems, which actually I already mentioned. So analyze normalizing flows for d equal to 1, constrained ones, and in general for d greater than 1. And both of these seem to require solving supervised learning for either moderate size networks or more than one hidden layer. Thank you.
Let's thank Navin. And there's one more question, last comment from Devavrat Devashi about the theorem seems to be about learning a general function. So what does it have to do specifically with normalizing flows?
Sorry, this theorem, the main theorem?
Yeah, it just seems to be something about learning a function with a sufficiently smooth, this complexity.
Oh, but we have to use the architecture that I mentioned, right? The unconstrained normalizing flow architecture. Did I? So this whole thing is for unconstrained normalizing flow. Does it answer the question?
Okay, but I mean, it could be. I mean, this would be the same as trying to learn some other function based on learning a network for its derivative and then doing quadrature.
But we used log likelihood, which gives us a lot of headache instead of using the other loss functions. And also because of the specific form of unconstrained normalizing flow, because also the log likelihood involved f prime and f, so the derivative of network. So all those things make it quite different from supervised learning result that I mentioned earlier.
Okay, so let's thank Navin again. We are already past time for the talk.
Sorry about that. Yeah.
No, that's okay. That's okay. It's wonderful. And so we should be maybe 1 minute. We should start the next talk again.
Thank you.
Thanks, Navin.